All right, so we're going to finish up section 7.5. We had started it yesterday, got through most of it, but we'll finish it up today. So we started by looking at the sum and difference formulas, okay, for sine, cosine, and tangent. Okay, some of them we derived. Okay, a couple of them I think we derived. A couple of them I just gave them to you because if we derive every single formula, it starts to take a really long time. But I want to look at this one. Okay, the tangent of alpha plus beta. And I want to see if we can figure out how are they getting all that stuff on the right. So I want to start with tangent of alpha plus beta. And I want to think of a way to rewrite that. Okay, how can you rewrite tangent in general? And I want you to try to think in terms of the identities that we would have learned just before we did the tangent sum and difference. Remember how you can rewrite tangent. Amanda? Yeah, you can write it as the sine over the cosine. So this is the same as sine alpha plus beta divided by cosine alpha plus beta. Any questions on that? All right, so what we're doing, this is a derivation of tangent sum identity. All right, now what do we have in the numerator on that right-hand side? What type of identity is that? Yep, that's a sum identity, specifically with a sign. And how about in the bottom? That's another sum identity. And both of these, we had already figured out. Either I gave them to you or we figured them out before we got to tangent. So let's look up sine of a sum and see what that is. So let's go back. Actually, I have sine of a difference. Sine of a sum, it's almost the same thing as sine of a difference. What's the only change in the formula I have on the board there? To do sine of a sum. Addition. Yeah, it changes to addition. So it's sine cosine plus cosine sine. So let's start with that. So we have sine cosine plus cosine sine. Okay, that's how every sine sum formula works. Now you just have to fill in the arguments. And the order is always first, second, first, second. Okay, that's for the sine identity. All right, so first is alpha, beta, alpha, beta. Okay, all of that is divided by the cosine of a sum. Can somebody remind me what's the formula for cosine of a sum? Amanda?
Cosine of alpha, cosine beta, minus sine of alpha.
Yeah, so it's cosine, cosine, sine, sine. And with the cosine identity, if it's addition, you put a minus in the middle. So alpha, beta, alpha, beta. Okay, any questions on that? Okay, but that still doesn't look like what's below the question mark. They are the same thing, but there's a little work to get that to look like the other thing. What could you do if you had, just to simplify it, if you had something like, let me simplify it without trig for a second. A plus B, let's say over, how do I want to do this? Well, I want to break this up, okay, into different fractions. Okay, instead of basically, I have like a common denominator right now. Like one big fraction. Anybody tell me how I could split that up so that instead of one big fraction, I have two fractions? Like, how could you split up something like this? What could that be if you split it up? Yeah?
A over C plus.
Yeah, you can take that and basically split it like that. That's the trick you have to do here. Okay, if you do that, we should get some stuff that's going to cancel out. All right, so let's try that trick and see what happens. Okay. So we've got. Does everyone understand what we just did? That idea? All right. So let's take and try that here. So. So I'm going to take the sine alpha, cosine beta, pretend like that's the A. Okay? And we're going to take and divide that by everything that's in the bottom. Okay, so we'll put that entire thing. Cosine alpha, cosine beta, minus sine alpha, sine beta. Now I want to just, before I even do the other part, I want to look at that for a second and see if there's something there that I could cancel out. Anybody see anything there that would cancel out? If I don't see something that's going to cancel out, I'm going to pause for a second and take a look at it, because I know we're right up to that step. Okay, but before I keep going with this, I want to double check that it's actually going to go somewhere and do something. If it's not, I might take a step back and try something else. Let's pause and look at that for a second. All right, so we started by trying to split that fraction up, but looking at it, it just didn't look like that was really going to go anywhere. That's why I stopped before we got too more involved. The trick that you have to do here to get it into the tangent identity is basically, if you have a fraction like this, dividing all three terms by the same thing. Divide a by x, b by x, and c by x. Okay, how do you figure out what to divide by, though, to make it what you want? Well, we could figure it out because we already know the answer. Okay? We know what we're supposed to get for the tangent identity. But if you didn't know that, it would be a little harder to figure out. Here's the hint I'm going to give you. You want that to be a 1. Okay? So right now you have something plus something in the top, and you have something minus something in the bottom. It's exactly what we have right here. Something plus something in the top, something minus something in the bottom. How could you turn that into a 1? And if you do it to what I just circled, you have to do it to all three other spots.
Divide by itself.
Yeah, divide it by itself. And that's the hint, and that's the last step that turns all of that into the identity on the other page. So we're going to take sine alpha, cosine beta, and we're going to divide. Let me circle everything we're going to divide. That, and that. All four of those things, we're going to divide by what I just checked off. Okay, cosine alpha, cosine beta. Okay, and when you do that, a lot of stuff will cancel out. So we'll look at that in a second. Okay, I'm going to write in red what we're dividing everything by. What I put in black, that will be the original. So, cosine alpha, sine beta. And we're going to divide that by cosine alpha, cosine beta. So there's the top. And hopefully you might already see some things that are going to cancel out because they're the same in the top and in the bottom. Okay, so a lot of this is going to disappear. Okay, and in the bottom, we're going to have minus. Okay, each part of what's in the bottom, we're going to divide by cosine alpha, cosine beta, cosine alpha, cosine beta. Now in the numerators, just put what we originally had. Cosine alpha, cosine beta. And as Dave said earlier, you've got the same thing in the top and the bottom. When you divide them, what's that going to turn into? That's going to turn into a 1. And that was my hint at why we should do that. Because if it turns this into a 1, which is what it should be, maybe automatically it'll turn everything else into what it should be. Okay? That's my hope. And then the last part, sine alpha, sine beta. Okay, let's start crossing off everything that cancels out. Is there anything that cancels out in the upper left fraction? Yep, the cosine betas. How about in the upper right fraction? Okay, the lower left fraction? Everything turns into a 1. And the lower right fraction? Anyone see anything there? Nothing there. Okay, so let's start with this. What's sine alpha divided by cosine alpha?
Tangent alpha.
Tangent alpha. Okay, so that one worked. So we got tangent alpha plus what's sine beta divided by cosine beta? Tangent beta. So that one worked. The other one, we said everything cancels out, so that turns into a 1. So that one works. And the last one, we have minus. What's sine alpha divided by cosine alpha? Tangent alpha. And what's sine beta divided by cosine beta? Tangent beta. And that's where the tangent sum identity comes from. Okay, a little tricky to figure out. Once you know what to divide by, what I put in red, it's not too bad. But to figure that part out, that's a little tricky. Okay, but I'm just trying to show you, all these identities come from the more basic sine and cosine ones. Okay, any questions on that one? All right, let's, okay, we got into the double angle. This one I know we proved. Let's look at this one. Okay. I don't think this one is, this is a lot easier than the last one we just did. Okay, let's look at cosine 2 theta. Generally, once you derive something one time, you never have to derive it again. You can use that formula in that class, forever. As we get into more identities, on like the half angle ones I'm going to show you later today, we're not going to derive them. Okay, some of them start to get really a lot of algebra involved, so we won't. Okay. Any thoughts on how I could figure out where cosine 2 theta comes from? I need a way to rewrite what's inside there. Hopefully, if you tell me a way to rewrite it, it's using an identity we learned yesterday. Anybody think how you can rewrite 2 theta? Allie? Yeah, you could write it as theta plus theta. Now that's something we should already know how to work with. What kind of identity is that? That's a cosine sum identity. So we just did that a few minutes ago. What's the formula for the cosine sum? So it's cosine first, cosine second, and then it's minus. For the cosine identity, I'm pretty sure that's a minus. Somebody double check me on that. It is a minus. With the sine, it stays the same. With a cosine, it becomes the opposite. And then minus sine, sine, right? Yeah. Okay, now the first and the second, how do they compare here? The same. So theta, 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 theta. What's cosine theta times cosine theta? No, not 2 cosine. That would be like x plus x would be 2x. This is like x times x. Yeah, this is cosine squared theta. And what about sine times sine? Sine squared theta. Cosine squared minus sine squared. And that's exactly what we have right there. So that's one version of the double angle formula. Not too bad to figure that out. How would you change that into that or that? It's pretty much the same steps to do both.
Isn't the second and the third just pretty much the same? Just the one moved to the inside.
Yeah, but they've also gotten rid of one of the trig functions. So the top one, they have the cosine and the sine. In the other version, just a sine or just a cosine. So how could you change that into one of the other two? Does that top identity look similar to anything else? Something that we studied earlier? Think about it. If you're going to change that, you'd have to plug something into it. But we have other identities that look very similar to that. Can you remember the other one? Yeah? Which Pythagorean one are you thinking of? There is a Pythagorean identity we know that would do exactly what I just asked. It would change that top one into any one of the ones below it. Amanda?
There's like one that's like sine squared x plus cosine 2x equals 1.
All right, sine squared theta plus, what was the other one?
Cosine squared theta
Yeah, equals what?
equals
1. That's a Pythagorean identity. It's one of 3. If you use that on what we just figured out, it would change it into one of the other two. Let's try writing it just in terms of sine. Okay. So if I want to substitute for this, what is cosine squared using the identity Amanda just gave us? Well, Andrew? What's cosine squared? Yeah, using the identity Amanda just gave us. So solve this for cosine squared.
1 over sine squared. Oh no, 1 minus sine squared.
1 minus sine squared. So cosine squared is 1 minus sine squared. Make that substitution on what I just circled. I have 1 minus sine squared. That's just the part I circled, but what else do I still have on the end? Minus another sine squared. So what's 1 minus sine squared minus sine squared? You're minusing 2 of the sine squareds, and 1 minus 2 sine squared is exactly the second one. You could get the third one by replacing this instead of what I circled the first time. The last one, okay, tangent of 2 theta. I don't want to go through the whole proof of it, but how do you think you would start? If you wanted to figure out, well, actually, there might be 2 ways you could start. Can somebody give me one way you can write that differently? Yeah? Exactly. You could write it as sine 2 theta, because you know that, over cosine 2 theta, because you know that. So that's one way you could figure out the tangent of a double angle. What's a different way you could break up 2 theta? If you know the tangent sum identity, you could think of it that way. The tangent sum identity, that's the one we just derived. That's the one we had to think about for a second. It was a little tricky to figure out. But now that we know it, we could figure out 2 theta using that one. So once you start to learn the different identities, you can use it in different ways to figure out other identities. And sometimes there's more than one way to do it. So you could figure out this identity 2 different ways. Okay, so any questions on those? All right, so let's try a couple problems with the double angle. So the goal, when you have a double angle, an angle that's double, like a 2 in front of it, you want to rewrite it so that there isn't a 2 in front of it. All right? Just 1s in front of the x's. Okay. So is there anything there that already has a 1 in front of the x? We don't have to mess around with it. Amanda? Which one? Anything that already has a 1 in front of it. Yeah, this part is fine. Okay, it's already a 1x, so we don't have to do anything to that. But the other part, sine 2x, I want to rewrite it so that there's not a 2 in front of the x anymore. How do I rewrite sine 2x? And this is directly an identity. There's not anything too tricky with it. We just have to know what is sine 2x. Well, we could do that and then figure all that out again, but we've already done that. So we have the simplified version of what you just said. What is sine 2x? This is from yesterday. Tom, do you have that? Sine 2x. I mean, if we have to, we can go back and do what Quinn said, but we just did that yesterday, so I'm hoping we have the answer that we did yesterday from what he just said.
2 sine x cosine x?
Yes. The sine of double an angle is 2 sine cosine. So 2 sine cosine. Just make sure you switch the letter to whatever they use for the angle in the problem. And technically we're done. Okay, that's all they asked us to do. Rewrite it so there were no numbers in front of the x's other than a 1. Now, if they asked me to factor this, what could you factor out of that expression? Let's see, Pacey, do you see what you could factor out?
Would it be cosine x?
You can factor that out, and you can factor out a little bit more. Something else that the first and second term have in common.
Sine x?
No, they both don't have a sine x.
But 2.
But they both have a 2 and they both have a cosine. If you factor that out from the first part, what would you be left with? From this part? You're just left with a 1. Okay? Think about if you did distributive property. 2 cosine x times 1 is 2 cosine x. And 2 cosine x times what would give you what I just underlined? Sine x. So if they asked you to factor it, that's the factored version of the answer. If they didn't ask you to factor it, then you could have stopped there. It's really not too much work to just go that one extra step if they ask you to do it. Okay, so any questions on that? Okay, so when you do a problem that has a 2 in front of the x, it's not too bad. When you do the problems that have numbers higher than 2 in front of the x, they can very quickly become time-consuming. So this is one that it's asking you to do 2 things. It's asking you to, well, first thing is we have to rewrite it. So we don't have 2's and 3's in front of the x's. They don't tell you that, but you have to know, in order to solve a problem, you can't have a 2 or a 3 in front of the x. All you can have is an x. So the first thing I want to do is just practice rewriting this whole thing with just x's. Okay? And I would never give you one higher than a 3, because you're going to see a 3 is it's bad enough. All right. So the first part's not too bad. How can we rewrite sine 2x? So all my arguments are just x's. Okay, we could do x plus x, but we have a simplified version of that. What?
2 sine x cosine.
It's 2 sine x cosine x. When you're doing these problems, you definitely want to know the simplified version, because if you have to go back through and figure it out, it makes this problem almost impossible. All right, and now cosine 3x. Do we have a triple angle identity? No. There are triple angle identities. You can look up any identity you want, but we only have a double angle identity. So what can I do with cosine 3x to kind of break that 3x down into 2 pieces I can work with? You can break it down into 2x plus x. Now, the first part is pretty much going to stay the same the entire problem. We're not going to do anything else with it. The second part has a lot of stuff we have to do. What is the second part? What kind of identity is that? It's a sum identity. It's a cosine sum. So now, break down the second part using your cosine sum identity. And after you do that, you should have all 2x's and x's everywhere. You're not going to have 3's anymore. So that's how you do it. You break it down one step at a time. You take 3's and turn them into 2's, and then we can take 2's and finally turn them into 1's. All right, so we'll copy this. And can someone remind me again, what's the cosine sum identity? All right, so we've got cosine, cosine, switch the sign, and then switch plus to minus, and then sine 2x sine x. Okay, now that I've written down, what's the highest number in the argument, any one of these arguments? It's a 2. Okay, so now, I'll underline everything that's fine. That's fine, that's fine, that's fine. That's okay, and that's okay. There's 2 things here that are not okay. cosine 2x and sine 2x. That's cosine of a double angle. Do we have a formula for that? Yeah. Minus sine of a double angle. Do we have a formula for that? Yes. Okay, we've got formulas for both of those. And probably some stuff is going to cancel out here. Okay, we'll see. So we've got 2 sine cosine plus, what's tricky here is we have 3 options for cosine 2x. I'm going to come back to that. Let's do the sine 2x first, and maybe that'll give me a hint, because there's only one version of sine 2x. Maybe that'll give me a hint as to what version I should use for the cosine 2x to get something to cancel out. Okay. What's sine 2x? Amanda? 2, I'm just going to write it small underneath. 2 sine cosine times another sine. So what am I going to end up subtracting? So it's 2 sine cosine sine. Which one is squared? Yeah. Sine times sine is sine squared. So 2 sine squared cosine. Okay, that's the last part. 2 sine cosine times sine. All right, and now the middle part. There's a few different options we could try for the cosine 2x. Anybody have a thought which one of the 3 we should try? I have a thought, but it's because I had some advice. Yes?
I was going to say 1 minus 2 sine squared x.
Yeah, that's the one we should do. Any reason why you picked that one? 1 minus 2 sine squared?
Because we have another sine squared, and so they'll subtract each other.
So we have 1 minus 2 sine squared. The only thing I want to be careful of is when I put that in, put it in parentheses, because there's a cosine on the outside of it. Okay, now this is going to work out pretty nice. What do we have to do with this cosine on the outside? We have to distribute it. But once we do that, you're going to see something start to cancel out. Right? So this first part stays the same. Plus, what's cosine times 1? Cosine. And then cosine times negative negative 2 sine squared x. There's not really much you can do with it. Just it's negative 2 sine squared x times cosine. And we already have another one of those. So we're going to be able to combine those in a second. Okay, so that's minus 2 sine squared x times the cosine. Yep. And then minus another 2 sine squared x times the cosine. Questions on what we just did there with that distributive? Okay, because this problem, it's not an easy one. This is probably the hardest one we've done in the lesson. Because there's a lot of simplifying. All right, let's see. Does anybody see what all of those have in common? Or, actually, why don't we combine like terms first? What's minus 2 sine squared x cosine x minus another 2 sine squared x cosine x? it's just a minus 4. So I'm just gonna copy that. And all I'm going to do is change that to a minus 4, and I can get rid of that off the end. Okay, so that combined it a little bit. Now I'm going to ask the same question again. What does the first term, the second term, and the third term all have in common? Amanda? Yeah, so why don't we do what we just did in the last one, factor out what it has in common. If you take out a cosine from the first term, what are you left with? 2 sine x. What about if you take a cosine out of the second term? Well, we're left with something. A 1, yeah. And what about the third term? 4 sine squared x. Now, I'm just going to reorder that a little bit. What's in the parentheses? Because I want you to maybe notice something here. The cosine x on the outside it's important, but what's inside the parentheses is more important. Minus 4 sine squared x plus 2 sine x plus 1. Does anybody recognize this as similar to something you did in Algebra 1? That's a quadratic. That's all that is. Okay, that's a quadratic equation. Okay, it's basically, if you could solve this, that equation right there is exactly the same as solving what I just underlined up above it. It's something squared plus the something plus a number. Okay. For this part, I just wanted to go up to where you would start to use the quadratic formula. Tomorrow, I'm going to talk more about how you would finish that off with quadratic formula. But that's hard. I think getting to the point we just got to is harder than finishing that off with quadratic formula. That's very easy. But getting to this step is kind of hard. There's a lot of stuff you have to do. And you had to get lucky like Quinn did, and he picked the right identity to use for cosine 2x. If you hadn't picked the right identity, you might have gotten stuck there. Okay, and I would have looked at it and I would have been like, you know what, this isn't simplifying, nothing's combining. Maybe I would have gone back and tried something else. But he picked the right one right away. Because he noticed the sine squared and he noticed another sine squared. So, okay, so any questions on that? Good. So pretty a little bit challenging, but we'll talk more about how to solve that. Maybe if we have a little time at the end of class, I'll make something up. But I'm going to stop with this one. Okay, and the last set of identities I'm going to give you, which we're not going to prove any of these, are the half-angle formulas. So what these identities do, instead of having a times 2 in front of the variable, or in front of the coefficient, you have a divide by 2. And a half-angle formula gives you a way to figure out what it would be without the divide by 2, with just a 1 in front of theta. So what these kind of do, and like probably the most we would ever do with them, is it gives you another way to figure out cosine 15. Okay. Right now, you guys know how to do cosine 15 by doing it like this. Set it up as a difference. And if you know the difference identity, that's difference of a cosine, perfect. Just do it that way. But what could you let theta be here? And it would give you a different way to figure out cosine 15. If you let theta be 30, 30 divided by 2 is 15. You could use this formula to figure out cosine 15. Okay, so it's a different way to do it, besides a difference. So let's try it. let's find the cosine of 15, but let's not do it the way we did before. We're not going to do it as 45 minus 30. We'll do it as a half angle. And what would need to go in the top? 30. Right, these are identities I always look up because we've already got enough to remember. So it's the square root of 1 plus cosine divided by 2. 1 plus the cosine of my angle, which we substituted in 30, divided by 2. Now, when we did this before, a lot of square root of 6s would come up, 4s in the denominator came up, things like that. Right, so let's simplify it and see what happens. Okay, cosine of 30. What is 0.866 as a fraction? Do you remember that one? Well, what square roots do these involve? Square root of 2's and 3's. So it's something with one of those, but it's divided by something. Yep.
Square root of 3 over 2?
Yes, that is the square root of 3 over 2. Now, that basically is the answer, but that's a pretty awful way to read it, because you have a square root, and you have square roots within the square roots, and fractions, so it's kind of a mess. What could I multiply top and bottom by to at least get rid of my fraction within a fraction? Trevor? 2. Let's multiply the top by 2 and the bottom by 2. So what that's going to give me is the square root of, well, so you tell me, what would be in the top? Yep, just 2 plus the square root of 3, and then in the bottom? 4. Now, the bottom part, I could simplify that. Okay, because when you take the square root of a fraction, you take the square root of the top and the bottom separate. So I have 2 in the bottom, and in the top I still have that. Any thoughts on how I could clean that up a little bit so I don't have a square root under a square root? Yeah. Amanda?
Could you do 2 plus, the square root of 2 plus 3 over 2?
You're trying to use this denominator? Well, since we took the square root of it, it's no longer part of us.
I was doing because you have the square root and the square root, so those can cancel out.
Oh, the square root? No, a square root and a square would cancel out. Yeah, a square root and a square root don't cancel out. Have any other thoughts on how you could simplify that? Well, for now, I might stop with that. I mean, you could leave the answer like that if they didn't say to simplify it, but if they did say to simplify it, you would have to do a little work with that. You'd have to clean that up a little bit. And there's a couple ways we can do it. It might even be better to go back to the step we had before. And there's some different things you could try. You could try conjugates, multiplying the top and bottom of a fraction by a conjugate, and see if that causes something nice to happen. Yeah, there's a few different things you could try. But I don't want to get too bogged down with the algebra for that right now. I just want you to understand there's a different way to find cosine 15, right, using a half angle formula. Okay, there's your half-angle formula for sine. It looks pretty similar. And the half-angle formula for tangent. Any questions on those formulas? They're not always the neatest formulas to work with because you can end up with square roots inside of square roots, and you got to figure out a way to fix that. That doesn't look like it would happen as much with tangent theta over 2 because you don't have square roots in it. All right, so the last thing I'll do is just to kind of remind you of a few things for tomorrow, factoring and how quadratic formula works. So if you had something like, let's say, x squared plus 4x plus 3. Okay, how do you factor that? What's the first thing I would start by writing down? Oh, Jeff?
That'd be x plus 4, x minus 1.
Even before that, what would you have to put down? Just symbols.
Parentheses.
Yeah, put down your 2 sets of parentheses. And now I heard you say, what did you put in the first parenthesis?
X plus 4.
So we got to think of, let's start with this. What would you put in this parenthesis?
X.
Yeah, let's start with that. So the x and the x, I agree with that. And now I've got 2 numbers here that are both positive. Positive middle, positive constant. So we have to have a plus and a plus. Now, the next 2 numbers have to multiply to give me 3. And add to give me 4. So what would be 2 numbers that add to give me 3, multiply to give me 3, add to give me 4? Order is not important in this case, but sometimes it is.
3 and 1.
Yeah, 3 and 1. And now if this was an equation equal to 0, what would be the 2 answers to that equation? Negative 3 and negative 1. Okay, so just factoring a basic quadratic. So let's look at the same problem, except I'm going to change x to sine x. That's all I'm going to do. So now it's sine squared x plus 4 sine x plus 3 equals 0. How would I factor that? Yeah, it would be sine x and sine x. You need a plus and a plus. A what? A 3 and 1. There's nothing different about this than the last problem, other than you're replacing x with the word sine x. And now your 2 answers aren't negative 3 and negative 1. When you set this equal to 0, what would you have to do first? You would minus the 3. And now what would you do second? Yep. You would take the inverse sine. Any thoughts about taking the inverse sine of negative 3? What's going to happen? Think about the graph of sine. How low does the graph of sine go? It only goes to negative 1. It doesn't go to negative 3. So when you try to solve that, what's going to happen? There's no solution to this part. Okay, so we wouldn't have to worry about finding an answer there. Sometimes that happens. Okay, if you're not sure, you could type that in, and you would see it comes out to an error. Now this part, sine of x would equal what? the sine of x equal there if you set that factor equal to 0? So if we started out, our first step would have been that, and now get sine of x by itself.
Would you subtract
Yeah, you subtract 1. So sine of x is -1, and then x would be the inverse sine of -1, which you can solve. At this point, I don't really want to solve it. I just wanted to go through those steps. Okay. So any question on that? All right, now let's look at something like this one. Let's say 2x squared plus 3x minus 5. What's, you know what, let's actually just go like this. What's different about that one? Most likely, compared to the one I did up here. Let's see, Ayla, do you see what's different about that?
It's a plus and minus,
Okay, so yep, the signs are going to be different. What else in terms of solving it?
you would probably have to use quadratic.
Yeah, I tried to make up something random enough that it's probably not going to factor. Okay, so when you use quadratic formula, what would be your 3 letters? What would A be?
1,
Yep, 1 and B,
3,
C, 5. And you'd fill into the quadratic formula, you'd solve it. And when you use quadratic formula, what does it solve for? Like, what are you finding? You're finding x. It's very important we know where x is in this right here. Where is x? Sure. It's in the middle. It's right here. That's what you're solving for. Whatever is right there. Okay. So you're solved for this. You're not solving for x squared. You're not solving for 5. That doesn't even make sense. You're solving for whatever is right here. Okay, so let me write the same problem, just a little bit different. Sine squared x plus 3 sine x minus 5 equals 0. This is a quadratic equation. A is 1, B is 3, C is -5. You go through and do the exact same steps. But you're not solving for x in this problem. What are you solving for in that problem? You're solving for sine x. That's what you're solving for. Whatever is right there. You're solving for sine x. So when you're done quadratic formula, you're going to get sine x equals, and then we usually get something plus or minus something. And then sometimes there's a fraction in the bottom too. So if this was a regular quadratic, you would just have x equals, and then you might be like 5 plus the square root of 3 over 6. Well, now it's sine x equals. So this, after you finish quadratic formula, is not your answer. You have one more step you have to do with whatever you get from the quadratic formula. And what would that last step be? Huh? Yes. You have to take the inverse sine so you can solve for x. Right? If the middle was a cosine x, you would do inverse cosine as the last step. Okay? So I'm trying to show you that solving a trig equation that looks like a quadratic and the kind of quadratics you did in Algebra 1, it's the same process. It's exactly the same process. You just have to be careful at the very end. That's all. Okay, so that's the kind of stuff we're going to look at tomorrow. Okay, so if we're going to solve them algebraically, I can only give you problems that are set up like this. You have to have something squared, the something, and a constant. Okay, so it has to all be the same trig function. In algebra 1, if you had an equation like this, is that quadratic? No. You can't solve that because you have different letters. If you want to solve that using quadratic formula, you have to have all the same letter. Okay, so when we do trig functions tomorrow, you have to have all the same trig function. Okay, same idea. All right, so the homework tonight is just six questions on 417. So it's 18, 29, 31. Just do part A. I think there's a part B, maybe a part C. We don't have to do that. And then 37, 41, and 45. Okay, so I'll check that tomorrow. We'll finish chapter 7 tomorrow, and then we'll start chapter 8 on Thursday and test on Friday. Okay. Don't forget that progress reports close on Friday, so if you need to make up any work, come see me before Friday.